Well, class, this is another section in chapter 8. It's about rotational kinetic energy. Now, we talked about torque before, and torque can cause rotation, but if I apply a force like this here, and I move it a certain distance and let go, this wheel will gain kinetic energy. Just like that, and that's called rotational kinetic energy. And of course now the thing's going to spin until something slows it down, or if I apply a counter torque force again through a certain distance along the length of the wheel, and that'll stop it. Now, to get the formula for rotational kinetic energy, and then do a little experiment on this. By the way, these are problems in the textbook, and we'll point that out before we leave today. And there's one more segment, by the way, on angular momentum, okay? So what we actually have, let's go back and remember our old friend. Our old friend for now we're going to get a name, it's called translational. Kinetic energy. This is in chapter 6. It was 1/2 mv squared. And that was straight line motion. Well, in the case of rotation, though, we have a new friend. And I keep saying to you, as the semester goes along, you get tired of these new friends. But this is the rotational kinetic energy. And the proper way to derive this is probably using maybe calculus, but I'm not going to do that. I'm just going to do this instead. 1/2 the mass, but now we're talking about rotation, so what's V equal to? Well, V is equal to R omega. And that's going to be R omega squared. Now what I do is I write this out, 1/2 m R squared omega squared. But going back to what we talked about a few minutes ago, mr squared, that is the value of the moment of inertia, or the rotation, or says I. Now I depends on the object. If it's like the hoop here, or the ring, is just mr squared. If it's a sphere, like a bowling ball, it's 0.4 mr squared. If it's a disc, it's 0.5 mr squared. So each one is a little bit different. So now what I can do is I can write this formula this way. 1/2 I omega squared. Now if you roll something down an incline, then you have two kinds of rotational, or two kinds of kinetic energy. So we're going to go over here now, and my assistant can go over there, I think, and we'll do this right here. I'm going to let the sphere go, and hopefully it'll go straight down the board here, and hopefully it stops when it hits this piece of wood. I'm going to try it again, but now I'm going to try it with a sphere, with a solid cylinder, rather. It says solid cylinder. Like that. And finally I'm going to try a hollow cylinder. In other words, a piece of a pipe. And I'm going to put that here. I'm going to let that roll down the incline. Now there's certain problems in the end of the chapter which revolve around this. And I'm going to point out two of the problems right here. Some are worked out for you. On page 8-16, problem 13 is a problem involving this. So we have a choice. We're going to do it. Do you want to do it for the sphere, or do you want to do it for the solid cylinder, or do you want to do it for the hoop? All right, we'll do it for the sphere. All right, so I'm going to go up here again, like this, and let these two things go at the same time. Now this has a moment of inertia of 0.4 mr squared, 2/5 mr squared, so it has less rotational inertia than this does, because here all the mass is located at the rim. So I let these things go at the same time. the sphere should win the race. Of course it did, because it rolled off the table. Alright. But we'll try it again. My assistant is getting the sphere for me. Thank you, dear. Alright, so we'll give it a try again. This time I'm gonna roll this one, the sphere. I'm gonna roll the solid cylinder, and we'll see which one wins the race. It's always funny when it doesn't work. Well, that worked pretty good. And the sphere rolled off the table again. And the sphere will win the race because it has easier to rotate. So I'm going to go over here now and I'm going to do the problem, next problem that we're going to do. And my assistant can, you're photographing yourself now?
No, the sphere.
Oh, yeah, you're photographing me? Okay, fine. All right. For years, my students have always wanted to know what my wife looks like, okay? And there's a little picture of her, as I recall, in each lesson plan, a little picture when we were in Egypt. There's a picture of her at the Sphinx. What?
It's not there anymore.
It's not there anymore? Well, I'm sorry, that's a shame. Well, this is what we have. We have a problem like this, like that. Up here we have a sphere, and the sphere has potential energy. And then you let it go down, and the way down it gains kinetic energy. But two kinds of kinetic energy. One kind is 1/2 mv squared, and then we have our new friend 1/2 I omega squared. All right? So I'm just going to write it up here. We're going to say the potential energy at the top will be equal to the kinetic energy plus the kinetic energy at the bottom, because we actually have two kinds of kinetic energy, translational and rotational. So it's going to become mgh, that's our old friend for potential energy. Translational kinetic energy, 1/2 mv squared. I hope I wrote that down. I did, back over there. And this is going to be 1/2 I omega squared. Now I, though, is equal to, for a sphere, I for a sphere, is equal to 0.4 mr squared. So now I'm going to write this in. I'm going to write mgh, 1/2 mv squared, plus 1/2 times 0.4 mr squared omega squared. And this will be like problem 13 on page 8-16. But we're going to do the lab experiment in a minute. We'll see how that works out. Now, if you notice what happens here, m in each term, so I can divide each term by m, that will cancel out like that. And then you look over here and say, ah, there's an old friend from earlier. And the old friend is that V is equal to R omega, which means that V squared is equal to R squared omega squared. So now I'm going to rewrite this thing again. GH is equal to 1/2 V squared. And 1/2 of 0.4 is 0.2 V squared. Now going back to algebra, 1/2 plus 0.2, 1/2 is 0.5. 0.5 plus 0.2 is 0.7. So this becomes 0.7 B squared is equal to G times H. So now I'm going to go over here. And B is equal to the square root of G times H divided divided by 0.7. There was an earlier video that we took showing this, but we're going to do it again and see if it works out pretty good. And it's not the same as the one on page 8-16, but it's okay. So I need my assistant now to help me again by moving a little bit, because I have to get at the board over here, okay? So I'm going to measure this initial height. Well, this initial height right here it looks like it's about 7 centimeters. So H is going to be about 0.7 centimeters. So let me write that on the board. H is 7 centimeters. That's going to be 0.07 meters. Now we know what G is. G is 9.8 meters per second squared. And we have 0.7 right here. So the speed here at the bottom of the incline should come out to be the square root of 9.8 meters per second squared times 0.07 meters divided by 0.7. Okay. Now I need my calculator, although I think I may be able to do this in my head. .07 .07 divided by 0.7 should be about 0.01. That comes out to be 0.01. .8 meters per second squared times 0.01 meters, and 0.01 times 9.8 comes out to be 0.098. And that's meters squared per second squared. Now I have to take the square root . 0.098. That comes out to be about 0.31 meters per second. Now to figure it out so we can relate to it, we have to figure out the time. And we have to use this equation to do that. We already measured the length of the incline. That's 1.145 meters. We know this was 0.31. About time? Am I close? Divide by 2 times the time. So it's going to be 1.145 divided by 0.155. And that time should be about 2.31 seconds. And that's the end of this experiment.